Welcome to this video. We are going to finish off the integration problems in the chapter 7 review of the Stewart 7th edition early transcendental calculus textbook. Okay. There's 10 more, so let's finish it up. I'm not including the improper integrals in the chapter review, okay? So this is just the general integration problems. I don't know how else to classify it. Okay, let's just finish it up. Okay, we have this integral from 0 to ln 10. So this limit as ln 10 should give you a clue that maybe you should sub in something with e. But anyway, e to x squared e to x minus 1 over e to x plus 8 dx. Okay, so what can we substitute? Okay, remember our technique that we've been using? We substitute what's in the square root. Maybe that can help. Because if I substitute something as e, like the bottom, there'll be this derivative, but then how do I substitute in there? You'll still have the square root. So that might be an issue. Okay, so let's try subbing the whole square root. So u is square root e to x minus 1. Again, you could just differentiate from here, or we can make it look a little nicer. U squared is e to x minus 1. So 2u du is e to x dx. Okay, so we can sub this guy. E to x dx, we can sub in. How about e to x plus 8? So we can use this definition. Okay, if we add 9 to both sides of this, so u squared plus 9 is e to x minus 1 plus 9, this would reduce to e to x plus 8. So we can sub it in as u squared plus 9. So let's try it. Oh, limits of integration also. When x is 0, u is 0, because e to 0 is 1. 1 minus 1, 0, square root of 0 is 0. When we plug in ln 10 as x, that's e to ln 10, which is just 10. 10 minus 1 is 9. Square root of 9 is 3. So it looks like we are on the right track in terms of the limits of integration even. Okay, so e to x dx, that's just 2u du. Okay, that's here. Square root term is just u, so that's all on the top. And then e to x plus 8 we found as u squared plus 9. Okay, so we can simplify, combine those two u's, u squared, I move the 2 outside, divide by u squared plus 9. So you can do long division here to simplify this, this rational function. Okay, you could use a different technique, which I think I use in the next problem if I remember correctly. But so in this problem I did long division. Okay, remember if the degrees are the same, you can simplify by dividing through. Okay, so u squared goes on the inside, u squared plus 9 goes on the outside. We can have one factor of u squared plus 9 in here, so minus u squared plus 9. We subtract the two rows, then we are left with minus 9. Okay, so that's the remainder. This is the quotient. The quotient plus remainder. So quotient plus remainder is minus 9, and then we divide the remainder by the divisor. Okay, this one is easy. That's just u, the integral of it. This guy is arctan. You should be able to hopefully recognize that. So 9 over 3, arctan u over 3. We evaluate from 0 to 3. Okay, and then we just plug in and simplify. So 2 times 3 minus, this reduces to 3. Right? And then we have arctan of 1, which is pi over 4. We plug in the lower limit. This is 0. Arctan of 0 is 0. Okay? So our final answer is 6 minus 3 pi divided by 2. Okay? Next, we have this integral from 0 to pi over 4, x sine x over cosine cubed dx. Okay? So I first thought, let's change everything, or I was thinking, yeah, let's change it to maybe in terms of tangent and secant. Okay, so how would we do that? Well, we can save one of the cosines here and lump it with the sine to make the tangent, and then this would follow through as cosine squared is left, which would be secant squared. Okay, so that's what I kind of decided to do. Why did I do that? I don't know. It just looked like it's nicer like this. And actually, when it's here, then I let u be tangent, du is secant squared, because I see something like that. But the problem is there's still this x, right? So when I do the substitution, that's just u du over here, the x is arctan of u. Okay, and then changing our limits of integration, when x is 0, u is 0. When x is pi over 4, u is 1. Okay, so we have the integral of arctan u du. This is integration by parts. Okay, so instead of u and v, I wrote p and q instead. Okay, so p is arctan u, dp is 1 over 1 plus z squared du. dq is what's left, u du, q is u squared over 2. Okay, so it's pq minus integral q dp. So that's half u squared arctan u, that from 0 to 1, and then multiply these together, that'll be minus half integral of u squared over u plus 1 plus u squared. Okay, so this looks very similar to the problem we just did, except it's just a 1 in that one. We can use the technique. You could use this upcoming technique that I'm going to show in this problem too, because we can just do u squared plus 1 minus 1. Why do I want to do that? Well, we can break this fraction out into u squared plus 1 over 1 plus u squared minus 1 over 1 plus u squared. Why do I want to do that? Well, this simplifies to just 1. Okay, and this is just, and that's easy to integrate, and this is just the arctan. So it becomes u minus arctan u. We evaluate this whole guy from 0 to 1. Okay. This guy over here, sorry. I already evaluated this over here. Okay, so by the way, so that's half times 1 times arctan 1. Arctan 1 is pi over 4. When it's 0, these were zeroed out. Okay. So where was I? I was down here. We do fundamental theorem of calculus. You in the end should get pi over 4 minus half. Okay. So to recap, this is all just tedious math, so I'll let you pause the video to look at that yourself if you want. The key here was, at least for me, I thought it's in terms of sine and cosine, which might be okay, but let me change it in terms of tangent and secant so that maybe I can see something else. Okay, to visualize it a different way, basically. Okay, so that's what I started doing here. So in order to do that, I had to take one cosine out to lump with this sine to make it tangent. Okay, so that's over here. So this guy is, again, is tangent, and this guy is just secant squared. Okay, that's how I did this one. 33, this one was an obvious trig sub because it was a something squared minus something squared, and there's a square root technically. It's square root of this guy, all of it cubed. That's what 3 halves power is. Okay, so I drew my triangle. Okay, you can even see I at first put theta here, but then I moved it there because I'm more comfortable with sine and cosine instead of actually cosine would have been fine. But anyway, okay, disregard the part. I believe I talked about this in the crash course video too, about changing the size or the angle. Okay, anyway, so I set up the triangle per this because I know that this is the hypotenuse and x has to be one of the sides, and the square root term has to be the last side. So I'm going to substitute everything here in terms of theta. I know that sine theta is x over 2, so 2 sine theta is x. Differentiate 2 cosine theta d theta is dx. Okay, square root term, how do I get that? Cosine is square root term over 2, so 2 cosine theta is square root term. Okay, we don't have that exactly here, it's cubed, so we cube both sides. Okay, so this would be 8 cosine cubed over here. Okay, so we substitute everything. X squared, that would be 4 sine squared. Dx is 2 cosine theta d theta. And then this one I just said is 8 cosine cubed. So that's down here. We simplify. There's 8 on top and 8 on bottom. Okay, so we would be able to cancel that out. Okay. Cosine divided by cosine cubed, so it's cosine squared on the bottom. Okay. So we can change this to tangent squared. And we know how to solve this. Tangent squared, we can change it to secant squared minus 1. When we do that, integral of secant squared is just tangent, integral of 1 is just theta, okay? And then plus c, and then we back substitute. What is tangent theta? We have to use our triangle. Tangent would be x over square root term. So that's here. Minus theta, what is theta? You can use any of the arc trig functions. We already have our definition here. We could just do theta is arc sine x over 2. And then plus c. Okay, so this is a classic trig set problem. Okay. Here we have integral of arcsine x quantity squared. Okay, so here I couldn't see anything I could substitute. It's not a rational function, so not partial fraction decomposition. It's not one of the trig integrals that you learn of sine and cosine or tangent secants. And then what was left? So we have by parts left. Okay, so and no trig sub. I didn't say that yet. Cannot be a trig sub. So by parts is left. So that's what I tried. U is arcsine of x squared. So that I put the whole thing in. Du is 2 arcsine x over square root 1 minus x squared dx. Why is that? Well, first we do the power rule. So 2 arcsine x to the first power. And then times derivative the inside. Derivative arcsine is 1 over square root 1 minus x squared. Okay? dv is what's left. dx. V is equal to x. Okay? So uv minus integral v du, that's integration by parts. So the integral is equal to x times arcsine x squared minus integral of 2x arcsine x over square root of 1 plus x squared. Okay? That's over here. Alright, so now I try to make a substitution because I see arcsine, I see its derivative. Let's let p be arcsine x. dp is 1 over square root 1 plus x squared dx. Okay? And when we substitute, we also need to substitute this x that's remaining. X is just what? Sine of p. Okay? By using this definition. Okay? So this, when we substitute, it becomes sine of p times p dp. Why is that? Well, once again, this x is sine of p, arcsine x is p, dp is dx over the square root, which is there. Okay? This is a classic integration by parts again. So we're going to do that one more time. I did the tabular method and I use even more variables now, y and dz. How do we pick our y? This is the one we want to differentiate. So p, differentiate to 1, differentiate to 0. Okay? You could have lumps to 2 in also. I didn't in this case. I don't know why. You could do it though. dz is whatever's left. Sine of p, we integrate it just as many times. Integral of sine is negative cosine. Integral of negative cosine is negative sine. Okay? Go diagonal, alternate sign. Okay? So it becomes minus p cosine p, that's here. Over here is plus sine of p, okay? And then plus c. Okay? I distribute this minus 2 to both terms. That's what I did in this line. And then I back substitute. P is arcsine x. So I have this whole thing here. I just it was from the back substitution. Okay? And what did I simplify here? Okay, so this one you can't simplify. This one, 2 arcsine x, cosine of arcsine x. Cosine of arcsine x we can simplify. I'll do that in a bit. Sine of arcsine x, that's just x. Okay? Alright, so cosine of arcsine x. Remember, this is pre-calculus. Or, yeah, I believe you learned this pre-calc, not algebra 2. Arcsine gives us an angle. So, some angle gives us a ratio, the sine of that angle would be x over 1. So we draw a triangle like this. Sine of that angle is x over 1. Okay, that's what arcsine gives us back the angle. The ratio of the triangle sides is x. Okay, so x over 1. And then we can use the Pythagorean theorem to get the last side. So cosine of that angle is square root of x, 1 minus x squared. Okay, so 2 arcsine x times square root 1 minus x squared. It simplifies to. Okay. Okay, so we had to use a lot of techniques here. You had to use 3 techniques here. By parts, substitution, and then by parts again. We have this integral 1 over square root of x plus x to the 3 halves. Okay? So I didn't see a substitution, the obvious substitution that we can do, and I didn't want to substitute this whole square root because I didn't see that it would really help. But what I did was I factored out x from both terms. That's what I did here. When we factor out x from this, it becomes 1. When we factor out x from here, we subtract the power by 1. So that's x to the half, which is square x, okay? Now, I can break this radical up into 2. So square root x times square root of 1 plus square root x. Here now I want to make a substitution. Now I see a doable substitution. U is square root x, du is 1 over 2 root x dx. Okay, so 1 over root x dx, that is 2 du. And then on the bottom we have square root of 1 plus u. Okay, that's after the substitution. You can make another substitution if you need, but I can already see what the answer is in my head. It's just power rule. So it'll be 2 times 1 plus u to the half power plus c. And then we have to back substitute u is square root x. So it's 4 times, 2 times 2 is 4. 4 times 1 plus square root x to the half power plus c. Okay, that's how we do this one. This one's just some algebraic manipulation to be able to do a substitution. Okay, 36, we have this integral of 1 minus tangent theta over 1 plus tangent theta d theta. So when I see this, I don't see like something that can make it into tangents and secants. Well, if I multiply the top and bottom by like 1 minus tangent squared, it won't help because, or even 1 plus tangent, because the identity as 1 plus tangent squared is secant squared. So I can't really get that in this, I can't get 1 plus tangent squared that easily in this integral, in this, what's in this fraction, okay? So what did I do? I just changed everything in terms of sine and cosine instead. So that's what I did here. And then I multiplied both the top and bottom by cosine to get rid of this fraction. So it's cosine theta minus sine theta over cosine theta plus sine theta. Okay. Now here it's interesting because now I actually see a doable substitution. For let u be cosine theta plus sine theta, du would be, what's the derivative of cosine? Minus sine. What's the derivative of sine? Cosine. And this coincidentally is up here. Okay, so this is du over u. And that we know how to integrate, that's log of u plus c. So it becomes log of, what's u? Cosine theta plus sine theta plus c. Okay. So here we just had to change tangent in terms of sine and cosine, then do some algebraic manipulation over here to see a substitution once again. All right, 3 more. Integral of cosine x plus sine x quantity squared times cosine 2x dx, okay? So what did I do exactly? So this cosine x plus sine x, I reduced this because I skipped some steps, I guess. Because if we expand this out, it would be, let me use a different color pen to not confuse, cosine squared x plus 2 cosine x sine x plus sine squared x. That's if we expand this guy out, right? Cosine squared plus sine squared, that's just equal to 1. This guy, remember the identity, that's just plus sine of 2x. Okay? So that's what I replaced it with here, 1 plus sine of 2x. Cosine 2x dx. Here, I see a substitution we can do. You can let u be 1 plus sine x. Du conveniently is 2 cosine 2x dx. Okay? So it becomes, this guy's u, this guy is du over 2. Okay? So it becomes 1/4 u squared plus c. We back substitute 1/4 1 plus sine of 2x, quantity squared, plus c. Okay? This one, I again see a substitution, integral of 2 to the square root x divided by square root x dx. We let u be square root x. Du is 1 over 2 root x dx. Okay, so 1 over root x dx, that's 2 du. And then this is just 2 to u. Okay? 2 to u, that's a simple integral. It's just 2 to u over ln 2. Okay? And then this 2 we still have over here, plus c. So 2 over ln 2, 2 to the square root x plus c. That's the answer. And if you really want, you can move this 2 into the inside also. So it would be 1 over ln 2, 2 to the root x plus 1 plus c. Okay. 39. Okay, this one was complicated. Integral from 0 to half x e to 2x over 1 plus 2x quantity squared dx. Okay, how do we solve this? So I don't see it as a trig sub. I don't see it as something squared plus something squared. It's not a rational function, so not partial fraction decomposition. Clearly, it's not trig integral. Can I do a substitution anywhere? It's complicated because there's products of things, and there's e, and there's polynomials, and it doesn't seem like it. So what's left? Integration by parts. It might get a bit messy though, but let's just try. So I let u be x e to 2x. Why do I want to do that? I don't want dv to be that because I don't know how to integrate. I do know how to integrate that, but it's integration by parts again. So maybe let's try u as this first. Du is by the product rule, first d second plus second d first, 2x e to 2x plus e to 2x by dx. Okay, we can factor out e to the 2x. Okay, why don't I want to do that? Because it might help out later. Okay, so when we do factor it out, what's left is 2x plus 1 on the inside of the brackets, parentheses. Okay, dv is 1 over 1 plus 2x squared. So v is the integral of it. So how do we find the integral of this? This is just a substitution. P is 1 plus 2x. dp is 2dx. So it becomes half integral dp over p squared. So then it's just power rule. That's quite simple. Because minus half times 1 over p. You back substitute p. So it's minus half times 1 over 1 plus 2x. Okay. No plus c's needed because we're going to do the bigger picture now. It's u v minus integral v du. Okay, so u is here. uv, so v is here. So I wrote that there. Minus v du. So there's a minus, so it becomes a plus. So product of this guy times this guy. Well, notice that 2x plus 1 is here. Divide by 2x plus 1 is here, so they would cancel. So maybe that's a good sign. So we're left with half and e to the 2x. Okay, this very easy to integrate now because integral of e is just e, right? So it becomes 1/4 e to 2x after we integrate that. Evaluate the whole thing from 0 to half. Okay, because this was a definite integral, so I dropped some notation in this step, so my bad. This is just plugging in. X is half, and x is 0. Okay, when we plug in the lower limit, this one will go away, but this guy we still have a 1/4. Okay, the final answer is e over 8 minus 1/4. So you can look at the tedious math over here. The key here was I had to try something, so I tried integration by parts, and it looks like a kind of good candidate because I see a product of things. So integration by parts kind of undoes some of the product rule, right? So eventually it worked. Okay. And then last problem, we have this integral from pi over 4 to pi over 3 square root tangent over sine 2 theta d theta. So there's multiple ways to do this. When I was looking at the solution to check my answer, some people changed it all in terms of sine and cosine first. So the tangent would be sine over cosine, right? And this guy, you have to use the identity, which I also use, 2 sine theta cosine theta. Okay? And then after some manipulation, then you got it in terms of tangents and secants, and then it was solvable. Something like that. You can easily look it up. I found YouTubers doing this also in a different way. So I tried it as u is square root of tangent theta. I just tried a substitution. I didn't know if it would work. Maybe it would. So remember, we can square both sides. So u squared is tangent theta. So I differentiate it from here. 2u du is secant squared theta d theta. Okay? So square root of tangent is u. And then d theta is 2u du over secant squared. So 2u du is here over secant squared. So that didn't get canceled yet. Okay, and then 2 sine theta cosine theta is still there. So I'm stuck. Am I stuck? Well, the secant squared is the same thing as cosine squared on top, right? So, or we can, okay, first of all, we can cancel this 2 and this 2. Okay, so u squared du is on the top, okay? Or we can, secant squared is 1 over cosine squared. So we, on the bottom, are left with sine over cosine, actually. Okay? Yeah, so here, sine over cosine is just u squared, because sine over cosine is tangent. Okay, so tangent is u squared. So it becomes u squared over u squared du. So that's really easy. It becomes just du, integral of du, okay? So then, by the way, you have to change the limits of integration. When theta is pi over 4, u is square root 1, which is 1. When theta is pi over 3, u is what? Tangent of pi over 3 is square root of 3. So then we square root that again, so that's 4th root of 3. Okay, so that's how I got those limits. Okay, anyway, so back to here. This is just easy fundamental theorem calculus. It's just u evaluate from 1 to 4 root 3, the 4th root of 3. And then it becomes 4th root of 3 minus 1. Okay, so this is just how I solved it, which got the correct answer. Once again, you can look up other ways to do it. There are people that posted it also. Okay. And that's it for this chapter review for the normal integration problems. Hopefully this was good practice for you if you followed along to do it, or you did it beforehand and needed someone to solve it or explain the solution. Hopefully it was helpful. Please give this video a like if it was, and please subscribe to the channel to look out for more integration practice problems. I'll probably do the chapter section 7.5 next, the one on techniques of integration. There's lots of problems there too. So look out for that video. That's probably upcoming soon.